Okay. Okay, so we saw what degree is and how to compute it for undirected and directed graphs. So now we'll focus more on the undirected graph and do some what is called the degree distribution. How to get what is called the degree distribution of the vertices in a graph. And once we get that, we can come up with a plot like this that I showed earlier. Okay. Okay, so by degree distribution, what I mean is the probability distribution of the degrees of the vertices. So, given some graph like this, what I want as an answer for this question is what is the probability that if I pick a vertex randomly from this graph, what is the probability that if its degree will be say 2? Okay, so that's what we want to find, this pk, which is the probability of finding a vertex with a degree k. Okay, so again, given a graph like this, what we want to answer is if I just pick a vertex from the graph, what is the probability that its degree is some particular value, and we call it as k. Okay, so it's called the pk. Now, how to find that probability, the pk values, is what you're going to see now. So the first step is to write down the degrees of the vertices. So these are the 8 vertices and these are the degree values. So once we get the degree values, which everyone knows by now how to do it, right? Just compute the number of neighbors. For node 1, its degree is 3 because it has 3 neighbors. Node 2, its degree is 3. Node 3, its degree is 2. Node 4, its degree is 5. Node 5, its degree is 4. Node 6, degree is 3, and so on. So compute the degrees of the vertices, and then what you do is find out what are the degree values we have got. So the degree values we have got are like 2, the unique values 2, 3, 4, and 5. There's no vertex with degree 1, so we can skip 1. So the unique degree values among the degree values of vertices are 2, 3, 4, and 5. Those are the different values. Now what you need to do is count the number of nodes that have the specific degree value. So how many nodes in this graph have degree 2? So you can again go to this basic data. So there's one node with degree 2, another node with degree 2, another node with degree 2. So there are 3 nodes that have degree 2. Okay, how many have degree 3? One node, another node, then third node. So there are 3 nodes that have degree 3. How many have degree 4? There's only one node that has degree 4. How many have degree 5? There's only one node that has degree 5. So these are the number of nodes that have this particular degree value. Now if you want to cross check what you have done so far is right or wrong, just sum the number of nodes, and it's going to be 8, and that's the total number of nodes, right? So if you counted the nodes wrong, the sum will not be equal to the number of nodes. So you can cross check. Okay, so that's the second step. The third step is basically then divide the individual values for the number of nodes by the number of vertices. So write down again the degree values 2, 3, 4, 5 and divide each of these numbers by the number of vertices. So 3 divided by the total number of vertices, which is 8, is 0.375. 3 divided by again 8 is 0.375. 1 divided by 8 is 0.125, and another 1 divided by 8 is 0.125. So these are the pk values. That is the probability of finding a vertex with a certain degree. So that means the probability of finding a vertex with degree 2 in this graph is 0.375. And that's what, as I said, if I just pick a vertex arbitrarily, what is the probability its degree will be 3? It's going to be 0.375. What's the probability the degree of a vertex that I pick is 4? Is 0.125, and so on. So as you can see, The more the vertices have a particular degree, the probability of picking a vertex with that degree is going to be more. Okay. Now, you might, any questions so far before we proceed? Okay. So, now in a math class or statistics class, you might have seen a formula like this to compute the average degree given the k and pk values, right? So we know we can compute the average degree by just summing the degree values and dividing by the number of vertices. That is one way. And we'll get the same answer using the k and pk values. So this is the formula. K times pk summed over all the k values will give you the average degree. So that means multiply this 2 times 0.375 plus this 3 times 0.375 plus this 4 times 0.125 plus this 5 times 0.125, and the sum of these things will give you the average degree, which is 3. And you can cross check. We know two other ways already. One way is just to sum the degrees, which is 3 plus 3, 6, 8, 13, 17, 20, 24 divided by 8 is also 3. And the other way is 2 times what? The number of links divided by the number of vertices. So of course you need to know the number of links in this graph, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Probably I have done some mistake in counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 edges divided by the number of vertices, which is 8 times 2. So 2 times the number of edges divided by the number of vertices. So 2 times 12 is 24 divided by 8, which is also 3. So all the three approaches should give you the same answer for the average degree. Okay, so in exam I could ask you to use all the three approaches and come up with the average degree. So one is 2 times the number of links by number of divided by number of vertices. The other is simply sum all the degrees and divide by the number of vertices. And the third is computing the pk values, k pk values, and using this formula k times pk summed over all possible values of k. Any question on this so far? Okay.
No.
Good. All right. So this chart is then essentially the plot of the degree versus probability of degree, the k versus pk values. Now this is a smaller graph, so that's why we get a more like what you call line graph. It's still like a curve, but you see it's more or less like a line. So if you join all the 4 data points, you get a curve like this. Now we do the same analysis for a large graph. Okay, so you can try these as practice examples. These are very small graphs too. So this is a graph for which vertex 2 has degree 3, the other 2 vertices are degree 2, and this one has degree 1. So you can get the numbers, you can try it for practice. Okay. But for a very large graph like the football network or the airport network, if you do the similar approach of finding the degrees of the vertices and counting the number of nodes that have a specific degree and so on, and do all the calculations like we did, you'll get a kind of the expected curve. So this shows that majority of the vertices have degree. So this is the Poisson degree shape, Poisson shape, probability distribution shape. And the one property of a Poisson curve is the peak of the curve is also the mean, the average of the distribution. So the average of this distribution is like close to 11, and that is the average degree of the vertices also. Whereas in the scale free network, the average degree is going to be somewhere around 8 or 10. Okay, but the larger degree, the maximum degree goes all the way up to 140. Okay, so in the Poisson distribution, the degrees of the other vertices are more or less distributed around the mean, in the sense that if the mean or the average is also called mean. So if the mean or average is say 11 for this distribution, the vertices have degree, majority of them have degree 10. See, what is that, 30% or close to 30% have degree 10. See, that's what the pk values means, what percentage or fraction of the nodes have the degree. That's another way you can look at the probability. Okay, so even if they say there is a 40% chance that it will rain today, the chance means probability. That means out of 100, if in the range of 0 to 100, the probability that it will rain today is 40% or 0.4. So similarly, if I pick a node from this football network, the probability that its degree will be 10 is close to 0.3. Similarly, the probability the degree will be 9 is close to 0.05, and so on. So majority of the vertices have degree close to the average, whereas in the scale-free network, that will not be the case. So the average will be some value, say in this case 8 or 10, but there are several vertices that have degree either way. Very far from the average. There's some that are close to the average, but there are appreciably larger number of vertices that have degree away from the average. Okay, so actually that's why it's called scale-free network. You cannot really put a scale for the network. So in the Poisson case, we can say the distribution, the range of the degree values is say from the average plus or minus what is called the standard deviation. We'll see the details in another module, but I'm just telling that. So in the Poisson distribution, the majority of the vertices are going to have degree around the mean, means the average plus or minus some standard deviation, the variation. So this is the variation that I'm talking about. Whereas here the variation is quite large. So we cannot say the degrees of the vertices is the average plus or minus the variation. So that means there's no scale for this for this airport network to represent the degree. Whereas for this football network, we can give a scale k plus or minus the standard, the average plus or minus the standard deviation. That's what that means. That's a scale. Whereas here there's it's not possible to give such a scale. That's why it's called a scale-free network. Okay. So we'll see that again in more detail in another module. Now I also want to show you the distribution. So most of the times we will deal with Poisson distribution, and this is called the power law distribution. The scale-free distribution is also called the power law distribution. So similar to the airport network distribution which we just saw for K versus PK. And we don't really need this math expression, but I just put it here for completeness sake. So in a statistics class you might have seen this. So how to generate a probability distribution. So this is the what is called the probability generation function or density function. So P of k is given by this formula for the Poisson distribution, and this is for the power law distribution, that is for the scale-free networks. Okay, and there are two more distributions. So this is one extreme and this is the other extreme. So in between, so if the Poisson, the bell-shaped curve, so in the Poisson case, the majority of the degree values are very close to the mean. So this is the average or the mean, and majority of them are very close to the mean. So if you go farther away from the mean in either direction, the probability goes to 0. It should really come down. As a kind of more bell-shaped type is called the Gaussian distribution. You might have come across the normal distribution, and that's the equivalent to this Gaussian distribution. So it is also kind of Poisson, but it is more V-shaped like this. Okay. And the exponential distribution is kind of like power law distribution, but not very narrow like this, and not long tail like this, but it's kind of more like this. So that is the exponential distribution. So these two are kind of similar somewhat in the way they look at, these two are also similar in somewhat in the way they look at, okay, the shape of the distribution. Right, so any question on this so far? Okay, I'm not sure what the other two are doing. Okay.
No.
Oh, okay, okay. All right, all right. I was just seeing the red. So yeah, red is muting probably, right? Okay. Let me check. Okay, we can save this.